Hey everybody, part 2 time. Oh, I messed that up. There we go. Alright, so we're picking up somewhere. Where are we? Day 2, I think. Yeah. So day 2 homework, near the end. I did one of the word problems in the previous video. Looks like we did it twice. Yeah. So we did number 4. I did it once. Well, this was just part A, so whatever. Part B we did twice, because we talked about how one way to do part B is to just do it in your calculator. You can set one side to y1, set another side to y2, graph them together, looking for your point of intersection, and for this particular problem, it says predict when, so you're solving for your t value, which is the x value. We got 74 years, which means 74 years after 1910, which put it into 1984. That is not what you'll be doing on your quiz because you can't use your graphing calculator. So I did the problem again on the next page, and we talked about how to just solve it algebraically. So you'd set the whole thing equal to the 20,000, and then you're trying to isolate your exponential, so you divide by this coefficient. And that reduces down. We can divide by 100 to kill the 2 zeros on the end. Then you can chop the 200 in half and the 42 in half to get 100 over 21. And then I just leave it. You know, you have your 4 function calculator, but it's easier to leave this as a fraction than to turn it into a decimal, so I would leave it alone. And at this point, you're just looking at an exponential, which, you know, exponentials can be converted into logs. The base of the exponential becomes the base of the log. What the exponential equaled becomes the thing you're taking the log of, and the power of the exponential becomes what the log is equal to. So I'm just doing it in symbols here, right? Heart and lightning bolt, star, whatever. But you really quickly can just convert this to a log, and then you're done. This is your answer, this log expression. You don't have to give me the 70 point blah blah blah. You would just give me the exact value, which has to be left in terms of the logarithm. So the answer you would give me is log base 1.0225 of 100 over 21. So let's do that again for the next one. So radiocarbon dating, they gave us a function. Here it is. It says estimate the half-life of carbon-14. So this is a good question. We've kind of talked about this before. We said that any exponential function that decays, you know, as long as the function is a decay model, then there's half-life there. Because I can certainly still find a point where I used to have 100 grams. At some point later, I'm going to have 50 grams. And so that amount of time that gets me from here to here, that's going to be half-life. I think they use lambda as the symbol for half-life. You guys that played the Half-Life video game, you can recognize that symbol, lambda. It's a Greek letter. Anyway, so that's exactly what you've got here. You've got a function where if I take this base, if you're wondering what e to that power is, well, the negative tells me it'll be 1 over e to some power. So it's going to be some fraction. It's going to be something less than 1. It's going to be decay. And so I can do this. I can figure out what my half-life's going to be. So anyway, enough backstory. Let's just figure out how to do it. To me, the easy way to do it is to recognize that the 20 represents the initial value. So if you're trying to figure out when that value is chopped in half, well, you know the half of 20 is 10. So you just set t equal to 10, and you go to solve from there. First thing you would do is divide by the 20, which unsurprisingly gives you 1/2. We're doing half-life, so of course it comes out to be 1/2, which really means that this initial value is irrelevant. We know that we just would want to be setting 1/2 equal to this expression, the base, whatever it is, to the power of t. So we get e to the negative 0.1230 and then 1216 t. So now we're converting to logarithmic notation from here. We would end up with the log base e of the 1/2, I guess, equals negative 0.00012116 t. Alright, So first of all, log base e can be more efficiently written as just the ln of 1/2, which we don't know what that is. That's an ugly value, so you'll just leave it as ln, and that equals this. And so to get your final answer, you just divide by that. So again, in the absence of a calculator, you can just give your answer as, you know, the time equals the half-life, which is going to equal the ln of 1/2 divided by negative 0.00011216. And so this expression is your answer. It's kind of unsatisfying because you have no idea what the approximate value of that is. That could be 2 minutes for all you guys know, or 200 years for all you guys know. But you don't have a calculator, so too bad. Like that's just your answer, and deal with it. Now, for the curious, sure, we can bring up our calculator and see what it is. How do I do that? I pull this up here, and then we update. There you go. There's your calculator. So just because I'm curious, move that over. It doesn't seem to have moved. Why didn't it move? I guess I have to move it here. Okay, my bad. I'm going to cover my beautiful face for a moment. Okay, so let's evaluate this thing. Clear? So the ln of 1/2, we can do that easily. And that's this number. We're now going to divide that by negative 0.00011216. And we get that. And you guys hopefully did this problem. We did it in class. You should already have this answer. But the 5,700 years plus a little bit of change, that's the approximate value of that. So we could write that down. 5,700 point blah blah blah. 224 if we're rounding appropriately. Okay, let me turn this calculator back off. Okay. And we know that because our t variable is defined to be years, we know that these are years. Again, you'll give me this expression. You don't have to give me this decimal. So there, moving on. To the next one, a radioactive decay problem. This time you're given the half-life. It says the half-life of a certain radioactive substance is 65 days, and there are 3.5 grams present initially. So express the amount of substance remaining as a function of time. Fine, we can do that. If they're saying substance, then sure, we'll say S of t. It's going to equal the initial amount of substance, which will be S sub 0, times a base of 1/2 to the power of time. But we have to divide that time by our half-life, so 65. So there's your model. That's part A. Then in part B, it says, when will there be less than 1 gram? So that's an amount of substance. So we'll just set that equal to 1. We know the initial amount is 60. No, we don't. We know the initial amount is 3.5. Then we've got the 1/2. Then we've got the t over 65. So to solve this without the aid of a calculator, you're going to want to isolate your exponential chunk, for lack of a better word. And to do that, you'll just be dividing by 3/5. If you want to be a little cleaner about this, then your I'm saying 3/5. 3.5 is what I mean. But 3.5, please tell me you all know, is 7 divided by 2. It's 7 halves. So to work this problem cleanly, you could multiply both sides by 2/7. And that'll cancel the 2's, cancel the 7's. 2/7 times 1 is 2/7. So this is now a cleaner thing to work with. We've now got our base 1/2. We've got our t to the 65. So at this point, we're converting to logarithmic notation. So we're going to end up with a log base 1/2 of 2/7. And that equals t over 65. So to finally solve for t, you just multiply both sides by 65. And you can get it to cancel on this side, and over here you get your final expression. So your final answer is 65 times the log base 1/2 of 2/7. And if any of you paid super close attention in Algebra 2 and actually remembered it, then you might remember there's a little rule that you definitely don't need to remember. This answer right here is fine, but if you wanted to be super cool, then you might remember that you can actually take the reciprocal of your base. And so instead of a base of 1/2, you can have a base of 2, as long as you take the reciprocal of your argument. So that's actually a slightly better answer. I don't know, in my opinion. Log base 2 seems better than log base 1/2. It does not matter, okay? You could give me either of those, and I'm sure most of you would give me this. I'm actually sure that most of you would give me what? 1 divided by 3.5? From way back when. I converted 3.5 to 7/2 and all that, right? Here's what I wish you guys would do, though. If you see a decimal, you just multiply by the power of 10. That makes it not a decimal anymore, right? If there's only one decimal place, then I just multiply by 10. If there were 2 decimal places, I could multiply by 100. But you can make it so that your fraction's not a decimal anymore. You now have 10 over 35. Those are both divisible by 5. And then lo and behold, there's your 2/7, right? It's actually pretty easy to turn a fraction that contains a decimal into a fraction that doesn't. And then you've got a much better looking answer. I mean, again, I harp on this. I don't mean to harp on this, but for sure, this is what an honors pre-calculus kid should be saying. An honors pre-calculus kid should not be satisfied giving me a 1 over 3.5. That's ugly in the eyes of a mathematician. So the 2/7 is great. And again, this little trick of taking the reciprocal of the base and taking the reciprocal of the argument, it's another way just to clean your answer up. Not mandatory. I wouldn't punish you. But if you kids are serious about like learning, then you'll do it. Anyway, that's T. So this is what you're supposed to give me. You'll just give me this because you don't have a calculator to evaluate this. But again, if anyone's curious, we can pull back our calculator, which is here. Bring it back. Update the thingamabob. There it is. You can't see me anymore, but at least you can see the calculator. So we are gonna just type this in. What do we want? Log base 2. So to get a log base 2, we're gonna go math alpha A. Math alpha A is sort of the shortcut. But I'm gonna do log base 2 of 7 over 2. And then just to prove the haters wrong, if I go math alpha A, if I do the base of a half, and then the 2/7, you guys will just see that, yeah, I'm right. That if you take the reciprocal of the base and you take the reciprocal of the argument, you do end up with the same answer. Okay, anyway, the only other thing now is multiply that by 65. So your final answer is 117.478. 117.478. 117.478. Okay. 117.478. And what is this? Time? Time in a function where time is defined in days. So this is 117.478 days. And what did it represent again? Oh, right. It's the time it's going to take for our initial sample of 3.5 grams to decay down to a point that's less than 1. Which makes sense. This has real applications in the real world. Like imagine if there was a accident at a nuclear reaction site or something. Then, people are going to know when, there ceases to be danger, right? When the concentration of the radioactive material is low enough that humans could enter without risk. And maybe that's 1 gram, right? So maybe they know that they got to air the place out for 117 days before anyone could go back in safely. Like, that's legit. I know that not everything we do in math is legit, but this truly has applications. All right, moving on. So that was the end of that lesson. We go to day 3 now, where we formally start to introduce logs. By the way, I know that because this homework question was from day 2, you really weren't expected to do logs. This explains why we were solving this equation before by just graphing in the calculator. We literally had not learned logs yet. But now that we have, you guys should be approaching these equations differently. You should be solving them algebraically and applying logs, okay? So that's the difference. I'm not going to go through the notes. I will go through the homework. So I think I did most of these too, and that's fine. You guys watch these videos, I think, knowing that you're going to hear me repeat myself. I think that's what you come here for, is to hear me repeat myself, hopefully. You can always fast forward. So for number 1, for any of these, we said that to evaluate these logs that aren't sort of straightforwardly obvious, you're going to convert to exponential notation, meaning you'll take your base of root 5 and you'll raise it to the power of x, and you'll set that equal to the 25 root 5. For a problem like this, you're hoping that you have a common base, and we do have a common base. That common base is 5. So root 5 is 5 to the 1/2. And that is being raised to the power of x. Over here, both 25 and root 5 have a common base of 5, so the 25 can go to 5 squared. And the root 5 can go to 5 to the 1/2. So now you got to remember your rules of exponents. When you've got a power to a power, you're going to multiply. So you get 5 to the 1/2 times x. But over here, when you've got an exponential times an exponential, you just keep the base and you add the powers. So it'll be 2 plus 1/2. So that means, well, 1/2 times x, if you put the x over 1, then you multiply the numerators, multiply the denominators, you're getting x over 2. So this is 5 to the x over 2. Now here we're adding, so your best bet is to get that common denominator. So your 2 we can express as 4 over 2, and then 4 halves plus 1/2 is going to be 5 halves. So this is 5 to the 5 halves. Then we said there's a rule. What's it called? The one-to-one property? I think it's just called the one-to-one property. That since exponential functions are a one-to-one kind of function, that if the bases are the same and the whole expressions are the same, then that would mean the exponents have to just be the same. So you're not really canceling the base. You're sort of using this property called the one-to-one property that just says that, hey, if all this crap is true, then it must be true that the x over 2 straight up equals the 5 over 2. At which point, all you got to do is multiply both sides by 2. And then the 2's cancel. The 2's cancel. You get x equals 5. So what does that mean? It means this log expression, if you evaluated this log, forget x for a moment, right? Evaluating this log, that has a value of 5. That's what we've really done, okay? So there's number 1. Let's do number 2. It looks like we're going to do the same basic thing with this one. Still, to evaluate a log equation, I'm going to want to first convert it to exponential pretty much every time. So you'll take your base of 2x and you'll raise it to the power of 2. You'll set that equal to 1 over 25. And I definitely heard questions about this in class, and it's mostly because people from here, I think they tried to divide by 2, but you're forgetting. You're raising this entire base to the power of 2. So this 2 needs to get squared and become a 4. This is really 4x squared equals 1 over 25. At which point the math becomes a lot cleaner, because now to kill that 4, I could divide by 4, but dividing by 4 creates a complex fraction, which nobody loves. So instead, just don't do that. Just instead imagine multiplying by the reciprocal of 4, because multiplying by 1/4 just feels cleaner. Obviously you could do it either way. But we get the 4 to cancel, we get x squared. And over here we get 1 over 100. Now to solve, we're doing nothing more than just taking the square root of both sides. Just don't forget that taking the square root of both sides generates both a positive root and a negative root. So we get x equals plus or minus 1/10. Now don't forget that we do have the potential for extraneous solutions when we're working with logs. Logs have restricted domains, so if you're ever trying to take the log of a negative, that would be an extraneous thing you'd have to throw out. But here x is in our base. But our base has restrictions on the values that it can be too, and it can't be negative. So even though algebraically we got negative 1/10 as a solution, the base can't be negative 1/10, because then 2 times negative 1/10 would be negative 1/5. You can't have a log with a negative base. So throw that out. I would kind of want to see this, though. I'd want to see you saying, hey, I'm taking the square root, I'm getting two answers algebraically, but of course the only actual solution, I guess we'd switch to solution set at this point to show that our final solution is the positive 1/10 only. So there. Alright, that's 1 and 2. This boy here had a typo. I believe Ms. Butler said that we just want to make this a 2. That makes this problem much easier. But to solve, you're still going to immediately just convert to exponential notation. So that means our base of 2 gets raised to the power of 2 from over there. And then you set that equal to this quadratic that was in parentheses. And then 2 squared is, of course, 4. So when you are trying to solve a quadratic, you want to get it set equal to 0 right away. So you'll be subtracting 4 from both sides. And then what happens is you get 0 equals x squared plus 5x. And then these cancel, which sometimes freaks people out. But no, this is like the best case scenario for a quadratic. Because all you gotta do now, still broken. Hold on. That's not gonna fix it. You cool, bro? No, you're not cool. Okay, it's cool now. Alright, sorry for that. You're gonna just factor out x. So you get x times x plus 5. And you can see you've got your two solutions up here. You've got x equals 0 as a solution, and you also have x equals negative 5. Now don't throw the negative 5 out right away because it's negative. That is not what I have ever said about logs. I said you can't evaluate a negative. But you can't evaluate 0 either. But what happens when you plug in 0? You don't get 0. When you plug in 0, you get 4. And the log base 2 of 4 sure as hell is 2. So as I double check this answer, it checks out. It's not extraneous. And the exact same thing is going to happen when you guys check your negative 5. Plugging a negative number in doesn't mean you get a negative number out. So plugging in the negative 5 is going to give you positive 25 minus 25 plus 4. These cancel and you again get 4, and the log base 2 of 4 is indeed 2. So even though you can't do the log of 0 and you can't do the log of a negative, neither of these are extraneous, because actually when you plug them in, you're not still getting 0. You're not still getting a negative. You're getting the correct answers. So we can definitely say that our solution set is both of those values, the negative 5 and the 0. Box it up. All right, next one. I'm going to just assume I need more room for this one. Okay. Actually, I don't think I do. Let's do it in green. All right, again, I hope it's obvious that we're going to convert to exponential immediately. Our base k is going to go to the negative 3/5, I mean negative 5/3. And that's going to equal 1 over 32. Okay, from here, what do? Well, we're going to raise both sides to the reciprocal power. Again, what are we trying to end up with? We're trying to just have plain old k, right? Well, plain old k has a power of 1. So how do you turn a power of not 1 into a power of 1? You'd raise it to the reciprocal power. Because when you raise a power to a power, you're multiplying your powers. And when you multiply something by its reciprocal, you get 1. So that's the plan here, is we raise both sides to the power of negative 3/5. So okay, so k to the 1, or simply k, is 1 over 32 to the negative 3/5. So now just remember that this exponent essentially represents 3 steps. The first step, in my opinion, is resolve the negative by just taking the reciprocal of your base. So you now have 32 to the positive 3/5. Then the denominator represents taking a root, right? So you're going to do 5th root of 32. And you're going to cube whatever comes out of that. And the 5th root of 32 is 2. You are supposed to just know that. That 2 times 2 times 2 times 2 times 2 is 32. So the fifth root of 32 is 2. Now you're just cubing that. And 2 cubed is 8. Chun, 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 chun. So there's your answer. Is that the only possible answer? Yeah, I would say so. Alright, hope you're catching on. Let's do 5. Guess what we're doing? Converting immediately to exponential, like everything else. So you take your base of 7 and you'll raise it to the 0, and you'll set that equal to 16 root x. So 7 to the 0 is 1. And you'd want to be dividing both sides by 16. So I'm going to cut to the chase and just say the 1 divided by 16 is going to be root x. So now to solve, you'll square both sides. Square, square. And so you get 1 over 16 squared. 16 squared being 256. So 1 over 256 is equal to x. Yeah, that's all. Easy peasy. I don't think I'm worried about extraneous solutions. I don't think I'm worried about anything here. No, we're good. That's it. So let's do 6. Again, assuming I need more room. I'll just throw that over there. And we'll do this one. Okay, how do you do this? Well, I can't convert to exponential notation immediately because I've got this pesky 1/3 kicking around. So you'll want to clean up the 1/3 first, and you'll do that by just multiplying through by 3. So if you multiply by 3 and you multiply by 3 on the other side, then you'll get these to cancel, and you now have log base 3 of 2x plus 1 equals 3. Now you'll convert to exponential, so you'll say 3 to the 3rd equals 2x plus 1. Which means 27 equals 2x plus 1. And you're now just looking at an algebra 1 problem. So just subtract 1. You get yourself a 26. That equals 2x. Divide by 2. You got yourself a 13. That equals x. And we could always double check. Plugging that thing back in, you get 26 plus 1 is 27. Log base 3 of 27 is in fact 3. And a third of 3 is 1. So yes, it checks out. So that's that. I think there's a 7 and an 8 and a 9. So let's push through these. For 7. A little ambiguous, this. It's somewhat unclear as to what is being squared. Somebody might interpret this to mean evaluate the entire log and then square. I think I'm interpreting this to mean square this stuff first and then take the log. I think that's entirely ambiguous. I think the notation needed to be better. I'm going to go with this interpretation, and if this comes out to be really nasty, then we'll do it another way. Although, you know what, I should say, if we interpreted it the other way, we'd just be up a creek. Because if they did mean to be squaring the entire log, then our first step would be to take the square root of both sides, and we'd immediately end up with something imaginary. And so if this was the interpretation, then this would just have no real solutions. So that can't be what we meant. So yeah, I think it's going to definitely be safe to say that there's just some big fat brackets here, and we're doing the log of what's in parentheses, including the 2. So now that said, we can convert to logarithmic. Exponential notation, we'll do 10 to the negative 2. We'll set it equal to the x minus 1 squared. Okay, sure. So this becomes what? 1 over 100, because it's 1 over 10 squared, which is 1 over 100. That equals this. So basically, immediately after squaring this, you're now going to just go ahead and take the square root of this, and it's going to go right back down to 1/10, and it's going to equal x minus 1. Now I kind of lied, because guess what? When we took the square root, we generated a plus and a minus, so we have both a positive 1/10 and a negative 1/10. We'll now add 1 to both sides, and we get plus or minus a 1/10 plus 1 equals x. So now you got to solve this. You've got plus or minus 1/10 plus 10/10. So that means when the 1/10 is positive, you're getting 11/10. And when the 1/10 is negative, you're getting 9/10. Now, is either one extraneous? No, because when you plug these in, when you do 11/10 minus 1, you get 1/10. Then you square it to get 1/100th, and the log base 10 of 1/100th is -2, and so that checks out. When you do the 9/10, well, now you get negative 1/10, but you're squaring it, so it turns back into positive 1/100th, and then the log checks out. So both of those solutions are our solutions, and we can go ahead and give our answer in set notation, including both. So there you go. Yeah, that's fine. I don't know. Was that one hard? Maybe. Let's do 8. All right, plenty of room for 8. Well, where's my dumb head? Starts here and here. Okay, so don't go into that area. What are we doing? Converting to exponential immediately. Great. So we go 16 to the 1/2 equals 9x plus 5 over x squared minus 1. All right, again, a lot of people still kind of struggle with this. This means square root of 16, right? But we're not going to do the plus or minus thing because we didn't take the square root. That's not what's happening here. This isn't a plus or minus thing. We definitely only want the positive 4. And that's going to equal 9x plus 5 over x squared minus 1. So now you recognize this as a rational equation, I hope. And your memory kicks in and says you should just multiply through by the LCD, which is the x squared minus 1. So when that distributes in, of course, you'll get 4 times the x squared minus 1. And when it distributes over to this side, they cancel out, and you just get the 9x plus 5. Now seems as good a time as any to just point out to you guys that, yes, that does just mean cross multiply. Cross multiply has always been a crutch that just stood in for multiplying through by the LCD. All right? So cross multiplication is fine, but again, it's a very specialized approach that only works for problems that are exactly of this form. It has to be exactly fraction equals fraction. If you had fraction equals fraction plus another thing, then suddenly cross multiplication doesn't work, but multiplying through by the LCD still does, right? It's pretty analogous to FOIL. FOIL literally only works for binomial times binomial, right? And the second you want to do binomial times trinomial, FOIL goes out the window. But we still have a more generalized backup plan, which was just take the terms and distribute. You go first term onto the first term, middle term, last term. Then you go second term onto the first term, middle term, last term. Again, FOIL is exactly that. It's first, outer, inner, last. It's just telling you to distribute with some silly mnemonic that you should never have needed anyway. Cross multiplication is kind of the same thing. Okay, tangent over. Back to work. Let's solve this. Obviously, distribute and get 4x squared minus 4 equals 9x plus 5. Okay, now that you've got a quadratic, you want to pull everything over to one side, get it set equal to 0, and hopefully be able to factor. So you've got your 4x squared minus 9x. Then subtracting 5 gives minus 9, set it equal to 0. We hope we can factor, so we have to do the AC method thing. So 4 times negative 9 is negative 36. We're hunting for factors of 36 that give negative 9. My plan is still, if you can't immediately see the answer in your head, then just be systematic about it. I immediately see the answer. It's going to be negative 12 and 3. So yippee. But if you don't see it, then you just start at 1. You go 1 and 36 with a negative 36. That's not 9. You go 2 and negative 18. That's 16, not 9. You go 3 and 12, negative 12. Oh, that's 9. So you've got your pair now. If that still wasn't right, you could continue on. 4 with 9, 5 doesn't work. 6 with 6 is an option. But again, I've now listed every possibility. There's nothing left. After 6, you could try 7, you could try 8, they don't work. You could try 9, you get 9 and 4, and you're back to a pair that you already had. So you know that by being systematic, you've exhausted literally every possibility. But we did find it. It's these guys. So we know we can factor this. I am going to want a 4x and an x, as opposed to a 2x and a 2x. I'm not going to want a 2x and a 2x because nothing times 2 will make 3, except for 3 halves, and I don't want to introduce fractions. But to get a 3 and a 4, I can put a 3 here, and then 3 times 1 will make 3. And to get 12, I can take my 4 that I already have and put a 3 here. So my outer product is now the 12 that I want. My inner product is now the 3 that I want. By the way, I wanted the 12 negative, so this 3 should be negative. I wanted the 3 positive, so this should be positive. And I'm factored. I probably said I would never explain that again, but I did. So who are my solutions then? It looks like if I set this equal to 0, then I get negative 3 divided by 4, negative 3/4. And if I set this one to 0, I get 3. So currently there's 2 solutions. Is either extraneous? Maybe. We have 2 reasons to be extraneous right now because we have a denominator. If either solution made our denominator 0, we'd have to throw it out because it would be undefined. But the only thing that makes the denominator negative is 1 and negative 1. So we're in the clear on that. But if either of these values make this argument negative, then we can't take the log of it, and then it's extraneous again. So plugging in 3, 27 plus 5 is 33. And plugging in 3, 9 minus 1 is 8. My math was probably bad. 27 plus 5 is indeed 32. And so that means when we plug in 3, we're getting log base 16 of 4, which guess what, is a half. So that guy passes muster. I don't feel like checking negative 4/3. It's going to work. It's going to be fine. But sure, let's check it. No, I really don't want to. Fine. It'll be negative 27/4. And I guess we're adding to that 20/4. Maybe it's not fine. 20/4. So that gives me a numerator that's negative 7/4. But I think the denominator is going to be negative as well. And then the negatives will cancel and we'll be fine. So plugging in negative 3/4 gives me positive 9/16. Then you're subtracting 1, which is 16/16. So like I said, that's negative 7/16. So what can we do from there? We can definitely kill the negatives. We can multiply by 1/7 to kill the 7s. Then you've got 1/4 over 1/16. At which point you'd multiply by 16, cancel the 16s, and get a 4. So yeah, both solutions are great. Put a box around both of them. Alright, moving on. There's one more of these. Nope, I lied. I really thought there was a 9. I'm thinking of something else. Okay. Alright. So the next thing, where are we? We're at 40 minutes already. Should I break this down to a second or third video, I mean? There's no real reason to, but I guess I will. Okay, bye everyone.